Good morning, guys, again, and welcome to today is April 8th. I have to check the date. Anyway, this is physical science, and this is the day before the spring break. We will have our exam after the spring break, as I mentioned before. So let's get going with the concepts that we have in here so far. Let me share with you the screen first. So today we're covering, hold on, I think I shared the wrong thing in here. Okay, that's better. So we're still basically continuing with the basics of chemistry. We talked last time about basically basic ideas, the fundamentals. We're going to get into far more in depth a little bit. Chemistry is part of physical science. That's why we're exploring it. This is one of the second of four topics that we're going to be covering in this class. We covered physics. We're going to be covering the chemistry component of this class. Then we're going to get into geology aspect of it, and we're going to conclude it with astronomy. So these are the physical sciences that we're going to be covering in this class. So we're well into the second one right now. So the first thing we're going to introduce is the concept of the dot structure. So basically to focus on something called the valence electrons, the electrons that can actually interact with the outside world, because there are two types of electrons. There are the electrons the inner electrons that are tightly bound to the nucleus. They're strongly held to the nucleus. And then there are the outer ones that can be either given or accept electrons to the outer shell, or actually be shared in a sense with other atoms to form different kinds of compounds. So those are the ones that are part of the dot structure. So when you see the dot structure, you will see that the entire group will have a similar structure. The label changes because the element has changed, because in its different period actually, but the outer shell would look identical. So this is basically, it looks the same, and that's why they have the same chemical properties. How the ions are formed, basically, if it is an alkali or the alkaline metals on the other side, they basically have tendency to give electrons. You require energy, though, to do that. So they cannot going to give it freely. They need those electrons to be stable. And on the other side, the halogens, for example, they take electrons. And when doing so, they go to a lower state of energy. So one of them requires energy, the other one is willing to give it, and basically they combine. Sometimes that's not enough. You have to add to it something else, but that's basically how the process works. There are several types of bonds. The ones that are going to focus on in here are basically the ionic bond. Once an ion is formed, okay, then it becomes electrically charged. So if it finds another one of another type, another ion that has the opposite sign, they become basically two charged particles attracting one another due to Coulomb's force. However, this attraction is limited by the size of the outer shell, basically by the outer shell of the electrons in the outer shell, because then there is an overlap of those shells, and because of the Pauli exclusion principle, you really cannot push them any further. So there is a distance with which those ions, they become in a stable configuration, okay? Usually that's a few nanometers or a fraction usually thereof. So around the nanometer distance between the two atoms, you're in good shape, okay? So it's several orders of magnitude of the size of the atom, about 2, 3, 4 times the size of the atom. Then basically at that point, the two ions can stay stable. Bring them apart, they will attract one another through electrostatic forces. One of them is charged positive, the other one is charged negative, so they will attract. try to push them closer, and they will repel actually, because the outer shells now you have trying to overlap, and they cannot. So because there is a quantum effect actually that prevents you from further bringing them closer. So now you have a stable configuration at that point. Another type of bonding is the metallic bonding. In the case of the metallic bonding, basically the outer electrons for a metal, they are still bound to the nucleus, but they are kind of a little bit loose. So even with the small amount of temperature, they become actually free to some extent. Not exactly, but free. So if you have a bunch of atoms, one next to one another, they have all kinds of electrons floating outside, and those electrons, they don't necessarily belong to a specific atom, but they belong to the community of the atoms. And then because of this, ions still positively charged overall, and the floating electrons, they're negatively charged. This provides a glue, a bond of this basically atom. So this is another way of doing the bonding of elements by sharing basically their electrons in the entire structure. It becomes like a fluid basically of electrons, keeping everything together. Then there is the covalent bond. In that case, what happened is the following. You have an atom and another atom, and both of them have the same level of strength in terms of attracting their outer electrons. So what they do in this case, instead of one of them giving it to the other, because it can't, it has the same strength as the other one, and the other one giving it to the other one. So what they do, they share their electrons in this case. So none of them takes and none of them gives. So in this case, they say basically stuck together because of sharing. This is a very important process because it involves a lot of basically molecules that form this way. So the outer electrons in this case are being shared. For the most part, they spend their life near the atoms, but they actually, because of quantum effects, they float around. But because they exist in the middle, in the most part, they are actually shared and hold the entire molecule together. So this is another type of bonding. In addition to that, sometimes one of them has more affinity to electrons than the others. So one of them will attract closer the electrons than the other. And that's typical usually when you have different sizes of atoms, or have an asymmetry in this case. So they are not completely ionized and they are not completely shared. So they are somewhere in between, hence called polar in this case, because there is a net negative charge on one side and there is a net negative charge resulting from the motion of the electrons closer to the other one than the net positive and a net negative, resulting in what is known as a dipole. And a dipole is exactly when you have two opposite charges of equal amount separated by a distance between them. So in this case, you have the so-called polar covalent bond. Okay. So what happened in this case? You still have your atom in here structured well. Your molecule, I'm sorry, has this two atoms in it or more. And you have another one next to it. So the other one next to it rearrange itself so that it's negative, come closer to the positive of the other one, and then the positive from this one comes to the closer to the negative, and so on and so forth. And you have now two different atoms or more, two different molecules or more attracting one another because of the reorientation of their own dipoles, basically. So you have what looks like a positive and a negative next to one another, with a positive clearly separated from the negative. That's on one side. On the other side, you still have the same picture, a positive and a negative, with clearly the positive and the negative separated from one another. So this atom would reorient itself, and the other one would reorient itself so that the positive and the negative of these two molecules will face one another and they attract one another. So this is the dipolar, basically, interaction. Molecules that have this polarity, they tend to fuse with one another. Case in point, for example, water. Okay. And then we have other kinds of interactions due to the polarity in this case, because you can have an atom that is otherwise nonpolar, an atom that is completely neutral, does not have any preference for one way or the other for its electrons. A molecule that is otherwise nonpolar, a molecule that does not have one way or the other preference for its charges. They are sitting actually at the middle, and it's actually nonpolar. And you have another one that is polar. So what happened in this case, if the conditions are right, that this one will induce a dipolar structure. So although this one is neutral, so it's going to move the electrons in such a way that they are closer one way or the other to induce, in this case, a dipolar effect in it. So these are an induced dipole interaction. So you'll have a dipole interacting with an induced dipole. And there is even another one, which is an induced dipole interaction. So in this case, this molecule by itself is otherwise nonpolar. This molecule by itself is otherwise nonpolar. But because of the big structure of this one and the big structure of this one, the charges, because of the thermal agitation, whatever conditions you have in there, move one side or the other. So now you have an induced dipole in this one because of other effects, which will induce another dipole in the second one, and now you have interaction between an induced. Obviously, this one is going to be a super weak interaction because a dipole is kind of shielded charges in general. It's still neutral, but it's slightly not neutral from one direction. So it's kind of there is a shielding effect in this case, okay? So the purpose today is actually to describe all of these interactions, try to classify them in terms of their strength. Obviously, in this case, probably the strongest ones are going to be the ionic and also the covalent bonds, okay? Metallic bonding is a little weaker. Polar, namely whether it's a polar molecules or polar to induced polar molecules or induced interactions are going to be the weakest in this order, okay? So this is basically what we're supposed to do in this day today. Anyway, so let's get started. Usually the day before spring break, a lot of people don't show up. So this is not no different, but there will be assignments. So if even if you guys are not on class, you still have to respond to this one in here because it's important materials, okay? Atoms band together through their electrons. That's the only way that the interactions. So the electrons are the name of the game when it comes to when it comes to chemistry, basically. Okay. So to learn about bonding, therefore, we need to know something about how the electrons are organized. Electrons are as if they are some sort of a shell structure. So when we analyze them in the past, this is basically what we're looking at. The dot that you see in the middle, right there in the middle, is what we're representing in here being the nucleus. The first shell, which is the 1s shell, that is the energy level 1, will have at most 2 electrons, one with a spin up and another one with a spin down. So it's saturated at that point. It will saturate exactly when you have 2 electrons, one pointing up and one pointing down. And in this case, the exclusion principle is 100% respected, because in that state, the energy levels at that point, there is no, the L is equal to 0, the angular momentum is equal to 0. Now we're left with the spin, and the spin can be positive, up or down. So we are saturated with 2 electrons at that shell. The next shell, which is the energy level number 2, n equals to 2. Then you have in this situation, at most 8 electrons. The 2s shell, which is symmetrical, can have 2. And then you have the 2p shell, which can have actually up to 6, okay? So you'll have, because at that point, the angular momentum is equal to 1. So the angular momentum is equal to 1. That means its projection along the x-axis can have a negative value, -1, or a +1, or actually can have a 0 projection also still. For each and every one of these substates, you can have still a spin up or spin down for a total of 6, because you have 3, you have -1, 0, and +1. And because of the spin now, you have 6. 6 plus the 2s state also, that is 2 for a total of 8. So far, if you're counting how many electrons in here, you really have 10, because the inner shell has 2 and the outer shell has 10. Okay? And that is the neon, actually, on the periodic table. If you go to the next energy level, which is n equals to 3. By the way, that is actually the period that we were talking about. So the first one is period 1, the second one is period 2, and now we're talking about the third period. The third period, 3p, and 3 level in this case also has 3s and 3p, the same fashion, okay? In this case, though, the energy level 1, 2, and 3, and actually the outer shell in here has one of the levels from here. It has a 3D also in here. Okay, so it moves up in here too. So what you have in this the shell, the P is equal to 6, the S is equal to 2, and for a total of 8, and the D actually has 10 in it. So now you're filling the 3D in addition to the 4S and the 4P. And you continue this way, okay? This is the SPDF configuration. So this is actually extremely heavy ions because you have to count all of the elements in here. So if you have 32 plus 32, that's 64, plus 18, that plus 36, if you wish, that is 100. 100 plus, this is all of the elements, okay? The picture becomes fuzzy in here a little bit between the levels D, F, and especially G. And that is basically how the shell structure is. This is not really a realistic image. This is not how the atom looks like. It's not like an onion shell that basically you start to rip the shells in and out. Okay, so that is really a representation. This is the model only for how the electrons are more or less distributed. Okay, so if I'm looking at so it's just in terms of their energies. That's all. Okay, just in terms of their energies. So this is just how the energies are, and they're actually not spherical, all spherical symmetry. There is only spherical symmetry, probably this level, only the 2s level. And there is actually the 3s level, which is symmetric, has a spherical shape, I mean, spherical symmetry. But the other one, the 3p, for example, the 2p, for example, is not. And the same thing with the 3s symmetrical, the 3p is not, and the 3d is not. The 4s and the 4p are, the 4s is probably symmetrical. So this is just a model for the energy, that's all, okay? If you wish, if I look at the periodic table, this number, which is n equals to 1, n equals to 2, n equals to 3, n equals to 4, those are actually the different periods, okay? How well is packed those shells is actually the groups in the periodic table, okay? So again, this is a conceptual model so that you guys understand. It's not really how the atom would look like. So if you, it's not like an onion, okay? This is just in terms of its energies, okay? And the energies explain everything in terms of the interaction of the atom with the surrounding. What matters in here is, for example, if I'm looking at this atom that has how many? 18 plus 18, that's 36 electrons. This is saturated, of course. Then what matters in here is the outer electrons, and not all of them, as a matter of fact. As a matter of fact, in here, it's not all of the 18 electrons that matter, because some of them are actually more bound than the other one. So in this case, it's just the, what is it, the last 10, okay? So here is how the dot representation in here. If you look at the helium, for example, the helium has exactly 2 electrons, and both of them are sitting in the outer shell. So this would be the helium in here when it has both of them, okay? The next energy level is the neon, which has 2 plus 8. Here are the 2, the inside, and here are the 8 outside, okay? The argon has a 2 plus 8, that's 10 inside. Those are completely forbidden. They are not participating in anything, okay? Same thing with this 2 for the neon. They don't participate in anything. As a matter of fact, the entire 3 gases are noble gases in this case, or at least they're inert, all of them, okay? They don't participate in anything because of the fact that even their outer valence electrons, they're saturated, because this one has spin up, the other one has spin down, and they cannot give or take anything. It's very hard to do anyway. You require a lot of energy to ionize helium. Same thing with the neon, which is actually more, okay? Because you have more positive charges inside the nucleus. And the same thing with the argon. So all of these things are neutral, and they are neutral because of the outer shell is full. But if I take an element next to them, for example, from the halogens, they have 1 electron that is exposed at the end, the outer shell. Any of these ones in here, the fluorine, the chlorine, the bromine, all of them, they have 1 electron that can be added to them. They have a vacancy. They have room. They have for rent sign on their on their energy levels. The ones on the other side, though, like the oxygen, for example, they have actually 2 rooms, okay? So all of this entire group in here are similar, and so on and so forth. This ones, though, they have an extra electron they want to get rid of. So if this ones, they have extra, and the other ones, they have a 1 room, so they can work together to form a new molecule where this one jumps in there and we're good, okay? So again, this is an explanation of what I was talking about. So valence electrons, electrons in the outermost shell of an atom, these are the ones that can participate in chemical bonding. The ones that are inside, no. The ones that are inside that are gray, blue in here, they're too tight to the atom in terms of chemistry. You don't have enough energy to get into them, okay? The ones that potentially can work with, and not all of them, are the ones actually in the outer shell. So the dot structure notation showing the valence electrons only, because those are the only one that matters in terms of chemistry, okay? For example, for carbon, this is chlorine. I mentioned the fact that it has a vacancy of 1. So it says in here, you have an impaired electron that likes to be paired too. The other three basically locations, they are full, they are paired. One of them is spin up, the other one is spin down. That's it. You cannot squeeze in anymore because the next one you're going to put either going to be spin up or spin down, and that violates Pauli principle of exclusion in this case. You cannot have 2 electrons in the same energy state. They cannot both be of them spin up. They cannot both of them be spin down, because then they will be in the same state, quantum state, and this is a violation of that exclusion principle. So one of them up, one of them is down, that's fine. So this is saturated, this is saturated, this is saturated. This is waiting for a partner to basically be saturated also. Now this one for the carbon, and if I look in the periodic table, the carbon group, all of them have the same similarity. They all have 4 electrons in the outer shell. So if you're counting how many electrons carbon has, it has 6 actually. 2 of them are forbidden inside, but we don't represent them in here. But the outer ones, they are sitting in the outer shell, the energy shell. They have basically n equals to 2 in this case. So, but you have 1, 2, and 3. Okay, one of them is in the 2s, the other 3 are in the 3p. So basically, they are outside waiting for partners to bond together. Sometimes they actually bond together in here and there and form other kinds of chemical bonds for the energy levels that is available. We're going to look at them. Krypton, for example, is an inert. It's full. All of its outer shells, they are represented in here. And those are just the outer shells in here. But however, it has 18 valence electrons, and we're not representing 18 of them, okay? Because the other 10 actually sit a little lower, okay? So we're not representing them, we're just representing the outer shell. As a matter of fact, if you go back into the periodic table, krypton and argon look identical. You have 2, 2, and 2, and actually it looks like neon also. So they are all noble gases, and they have the same look outside. Chemically, they are the same. The letters in here change, but the outside in terms of the dot representation, they are the same. Okay, here is more on the dot representation, with the exception of hydrogen, which behaves sometimes like metal, sometimes like non-metal. Actually, it has its own basically classification. Lithium, sodium, calcium, no, what is it? Potassium, rubidium, silicium, all of these things have 1 electron in the outer shell. Obviously, there are more electrons in sodium. There are 11 electrons altogether versus 3 in lithium. But the other 2 in lithium, they are completely bound together. They are completely tied together, just like helium. So an ionized lithium is exactly like helium. An ionized sodium is just like neon, because it has 11 electrons. If you remove 1 of them, it has 10 left, just like neon. Potassium behaves like argon. Now, when you move to the next level, you have now 2 electrons, because you add 1 more in the second group. Now, when you add the second one, so you'll have 2 of them that are unmatched for the case of beryllium, manganese, calcium, strontium, and barium, okay? And the boron in this case and aluminum, they have 3. We have moved all the way to 13 because we are not representing this ones in here. Here is where we are right now. Okay, actually the second period. Carbon, nitrogen, oxygen, fluorine, and then we go to the inert gases in this case. Same thing, we keep on going. And if you look outside for this entire group, they have the same structure. Polonium is just like oxygen. Okay, bismuth is just like nitrogen, and so on and so forth. So all of these elements, they have the same chemical behavior because of their valence electrons. They are similar. Okay, valence electrons, they actually look the same. If we forget to include the letter inside, that this is carbon and this is silicon and this is germanium, you would not know exactly what we're talking about. You would have no idea, but you know that they are similar. Okay, so that is basically how this thing is working. Make sense? Good, very good. I mentioned this. Sodium, atomic number 11, that means it has 11 electrons, has only 1 valence electrons because the 10 of them are already basically full in everything else. So the next energy level is actually 3s1. Upon losing this electron, what other atom in the periodic table does the sodium resemble? Obviously, it's going to resemble neon. Okay. So if you lose 1, you're back here. Okay. So lithium, when it loses 1, it looks like helium. The correct answer is neon. When it loses 1, it's not going to be 12. It has 11 electrons already. And in here, for somehow, it's already the third group. It ends up in the second group. They're completely the same chemical. No, that's not true. Okay. An ion is an atom that has lost or gained 1 or more electrons. So that's basically what an ion is. It's charged usually. Okay, it is charged. So in this case, it's neutral. It has 11 protons and 11 electrons. Once it loses it's an electron, this electronic structure, yes, it looks like the neon, but it's not exactly a neon because it has a positive charge, net positive charge altogether. You still have 11 protons in here that are not impacted inside the nucleus. I mean, if you cannot get to the inner electrons, very hard to get to them. How about the nucleus, which is impossible, basically, using any chemical process to get into it? Even if you heat it up to extreme amounts of heat, at least on the ordinary level, you're not going to get into it. You have to have extreme high temperature and high pressures to probably reach the nucleus. And that can be achieved with the nuclear accelerators or nuclear reactors, or in the sun, for example. Yes, you can get into it for those extreme high temperatures and high pressures, but not in ordinary chemistry. There's no way you can get into it. So you still have a positive 11 charges, in other words, inside the nucleus. But for some reason, you lost this electron. Now you have a net of only 10 electrons. So the whole thing is positively charged in this case because it lost. On the other hand, this guy has an empty space. Okay, what is this one? This one is a fluorine or chlorine, one of the two. Okay. Yeah, it's the fluorine. Okay. Fluorine and chlorine have the same number of outer electrons. Both of them have room for 1 more. Okay. But the fluorine has actually 9, 10, 11. Okay. Chlorine is actually comes in later. So in this case, the fluorine can take 1 more because the outer shells in here are not, there is 1 electron that is not partnered. So it can take that of the sodium if you like. So it can take this one, the one that was given by sodium, and put it together, and now this one is filled. Now it behaves just like the neon. This is exactly like neon. Since it gained it, it moved up to the neon. Okay, but it's still it still has only 9 protons inside the nucleus. So there is a net negative charge now of -1. So both of this one, and this one are actually ions. So this is a positive ion, this is a negative ion, okay? This is how molecular ions form. So it's not just the atoms that they can become ions, it's actually the molecules themselves, they can become ionic. So here is a neutral hydrogen, a neutral water, basically, molecule. If it gains an ion, in this case a proton, that has somehow stripped its hydrogen stripped of its own electron. So if it gains a proton, so what happened in this situation? It becomes an ion, it becomes positively charged, okay? It takes the charge that was in the proton, and the entire molecule becomes hydronium ion, which plays a major role in organic chemistry, at least in the in chemical reactions in general, becomes positively charged. So the oxygen before, remember, it has 4 paired electrons now, all of them in use. One of them was already with this hydrogen atom. At least now we have 2 of them in here and 2 of them in here, but it still have 2 pairs of electrons that are not bound before the presence of this proton. So when the proton comes in here, it's going, the oxygen atom will pair 2 of its already had the bound electrons to it, and now that forms that bond. So basically it's sharing those 2 electrons with this one, but it still has 2 more that can basically in here. But the energy level now is so basically unstable, this whole thing, but relatively speaking compared to water, of course, which is more stable. But in this case, you have this structure here. Overall, it's a positively charged. If it finds, for example, another electron somewhere in here, or it can find another ion in here, it can interact with it and form basically bonds in here. But the thing with it in here, the biggest point in here, forget about what I was talking about, is the fact that you have an entire molecule in here that became ionized, just like as if you have an atom itself that is ionized, albeit the net charge in this case is positive, okay? So I could potentially have an OH in here that is negatively charged, okay? This water molecule potentially could lose one of its electrons, and I will be left with an OH in here that has an excess electron in here, so it becomes negatively charged. So there is potentially for that, and that's how we actually got this H plus in here to be formed this way. So again, the ionic bond is the interaction between 2 different ions of different size, okay? I mentioned that in the beginning, that if you bring, for example, sodium and fluorine, and you bring them nearby one another, they're going to attract due to electrostatic forces. One of them is positive, the other one is negative, to a point where at some point their electronic shells start to intermingle with one another, start to influence one another. At that point, the separation becomes stable. You cannot go any closer, okay? So there is a separation where the 2 can, I mean, you would ask, why would they stop at some point? Why couldn't they fuse completely? And that is because you still have those outer shells, okay, that start to deform actually when the two molecules, 2 atoms become closer and closer to one another. So they will attract if they are far away enough, and then at some point they're going to stop from the interaction. If you try to push them closer, they cannot. So if you try to freeze this substance closer, they're going to get closer because of the less thermal agitation, but they cannot get any closer. You cannot have practically 0 volume in this case because they are still made out, their outer shells, they still have electrons that repel one another, okay? So when you have an ion that is positively charged and an ion that is negatively charged, you can form a stable molecule. But it depends now. You have 3 electrons in this aluminum that are basically given, okay? Remember, aluminum has that belongs to the 3rd group in there with the 3 electrons. Not 3rd. I don't remember what the group is. I mean, it behaves like the boron in this case, it belongs to this group, 13th group, so I should say here. So it has 3 electrons that it can give. Oxygen at most can take 2. How are you going to form, in this case, the oxide? How is going to the oxidation of aluminum is going to happen in this case? Well, this one can give 3 and this one can take 2. So obviously you have to mix the numbers a little. You cannot just take them one on one, because then you will have an excess electron in here. So if you take one aluminum that has given 3 electrons, this can only take 2 of them. So you need to bring more oxygen in here to the mixture to compensate for the extra electron. But if you bring another oxygen in here, you will have actually 4 electrons that can be taken, because one oxygen can take 2 and an oxygen can take 2. But now with the 2 of them, you can only take 4. But this one has given only 3. So you have to bring more in here of this aluminum that you need to compensate for. So you bring actually 2 more now. But if you bring 2 more, this 2 more will actually give you 6 electrons. 6 electrons, but you just brought 2 oxygens in here. So each oxygen can take 2. So you accounted only for 4 of the 6 electrons that are given. So you need to bring another oxygen atom in here. So if you bring another oxygen atom, which will compensate for the last 2. So you'll have to bring 3 oxygen atoms actually, and combine them with 2 aluminum atoms, so that the 2 will give you 6 electrons, and the 3 oxygen atoms will take the 6. Each and every one of them takes 2, and now you have a stable molecule, which is an ionized format in this case. So if you put them together, the dots now fill correctly. Aluminum, aluminum, and the whole structure, and now you're in good shape. So now you have a stable molecule. So if you are math inclined, you use what is called the least common multiple of the 2 numbers. Where is it? So in this case, the least common multiple of 3 and 2 is obviously 6. Because 3 times 2, those are prime numbers, is 6. How can I make 6 out of 3? By multiplying it by 2. How can I make 6 out of 2? Is by multiplying it by 3. So the correct configuration is this one, Al2O3. So this is the most stable. Oops, Control Z, what did I do? Okay. This one will not work because I will end up with an extra electron. This is actually worse because I will have 3 times 3, that's 9, and 2 times 2, that's -4. Then I have +9 minus 4, then I will have 5 electrons floating in here and there. So this is not stable. I need to have a conservation of charge. Since I came up with 2 times 3, that's +6. And since I came up with 3 times -2, that's -6. +6 and -6 is going to be 0. So if you're a math inclined, it's the least common multiple of the numbers, and then you divide that in here, and you find this one, and you divide that one in here, and you multiply this. This is how you're going to form your compounds. Okay, so this is the proper way of looking. Obviously, this is what ruby and sapphire are. They're actually this oxide, aluminum oxide. Okay. If there are more common, basically, combination of aluminum and oxygen, probably the more scientific way of calling this name in here, it's dialuminum trioxide. Okay. But it's called aluminum oxide and comes with this different. This is what ruby and sapphire are. It used to be one of the most expensive and valuable, basically, gems, and people used to sell it and buy it with extreme high, basically, priced, until in the, I believe, in the 1800s, the process of how to form them in industry became so easy that their values basically stumbled. They became, like, now they're made into as much as you can make them out of, because it used to be a rare, basically, a rarity that they were expensive, just like gold now. Okay, that's why they're called gems. Okay. Here is another example. Now, here is another rule, okay, about this one. Manganese can give 2 electrons. Oxygen can take 2 electrons. Over here, bring 1 and 1. The 2 cancel the 2, and now I have a neutral molecule. Okay? So this is okay. The first one is good. The second one also is good. The third one also is good. So which one is it? If you are, again, mathematically inclined, it's the least common multiple. Since 2 and 2 are prime numbers with one another, then the least common multiple in this situation has to factor out that common that prime number between them. And actually, in this case, the least common multiple of them is actually 2, but you have to factor out that 2. So it's 2 divided by 2, it's going to be 1. So the correct configuration is MgO. So when I said earlier the least common multiple, it was for the primed numbers. They are primed with one another. 3 and 2 are primed. In other words, if you divide 3 by 2, the ratio is not 1. Is not an integer other than 1. Okay? So in this case, it's not correct. Okay? So in this case, it was actually the least common multiple, which is 6, and you divide 6 by this one, and you divide 6 by the other one. In other words, okay, the least common multiple of this one in here is 2. 2 divided by 2 is 1, and 2 divided by 2 is 1, so you're going to be MgO. But we don't really write the 1 because it's assumed already. So this is the correct formula for this molecule, okay? Because the 1 is already assumed in here, so you don't do it. So this is not the correct way of writing this molecule, not this one either, okay? Obviously, it's not correct in here. Does this make sense? Good. Everybody? Okay, very good. So again, in the metallic bond, and I mentioned that the outer electrons are held, yes, but not strongly to the nucleus. And this weak interactions allows the electrons to move freely, especially with temperature. Okay. This mobility of electrons account for many of metallic properties, like, for example, thermal conductivity and electrical conductivity and things like that. However, for the conductivity in general, it's not good to have really higher and higher temperatures, because then the molecules, the atoms on the way, they will be basically agitated and moving faster and faster, which causes this conductivity to go down and down. So the material becomes more resistive in this case. But again, it's the outer electrons that account for these properties. An alloy is a mixture of different metallic elements that has also the same, basically, it's being held by the same, basically, large number of electrons that are available. This is an example of an alloy. Okay, it's used in currency. Covalent bond is when basically the two, in this case, I have fluorine. Both of them have the same strength and the same basically affinity for their electrons, the same electronegativity, which is how well they attract electrons, okay? Then in this case, if I bring them together, this electron in here can fill this gap in here for this and satisfy the requirement for this fluorine atom, and the other electron from this fluorine atom will come in here and satisfy the requirement for this one in here. And this looks like now it has all of its outer shell full, and the other one looks like it has all of its outer shell full, and both of them seem to be in a happy, basically, energy levels, lower energy, basically get rid of that excess energy, and it looks like it's a stable molecule in this case, and that is how the fluorine gas is formed. Okay. The trouble with that is, of course, as I said before, is that electrons in quantum mechanics really don't sit still. They're moving constantly. So all of these electrons, actually, even the inner ones, they're in constant motion, and even the nucleus itself is actually in constant motion. So what's going on really practically is that if I look for the probability of the presence of these two electrons, I will find them mostly near the middle for the most part. So the probability of their presence is extremely high in the middle than on the outskirts of on one side or the other of these two atoms. So there are 2 electrons within. So nobody gives, nobody takes. They share, okay? So there are 2 electrons within a single covalent bond. So this is the covalent bond. It's completely opposite to the ionic bond. The ionic bond is, there is a donor and there is an acceptor. In the case of covalent bond, there is none. Both of them have the same affinity for their electrons. This is why, because when we do the representation, we don't represent them as basically electrons, we separately represent them as lines. For example, in the case of the fluorine, this is how this looks like, okay? That this is a covalent bond between the 2. It's not like you have 2 ions separated from one another, okay? They're held together by the shared electrons. So it's always have to be a paired number of them. For example, in the case of the oxygen, it has 2 covalent electrons. So in this case, you can form 2 lines in this case, okay? So it can bring one hydrogen on one side and another hydrogen on one side and share. And as I was saying before, there is a polar molecules. So this is actually going to be slightly polar in a sense that the electrons will actually come closer to the oxygen than they do from the hydrogen. So they move away from the hydrogen because there is far more charges in here than on this side. Nitrogen can have 3 of them. That is what ammonia is, okay? Because you have hydrogen and hydrogen and hydrogen combining with the nitrogen to form NH3. Methane, on the other hand, remember, carbon has and the outskirts has 4 of them, so it can share its 4 electrons with the oxygen, with the hydrogen, and this is actually nonpolar because of the fact that it's symmetrical. Look at the structure; it's symmetrical. So even if the charges move closer to the carbon in here, this charge also will move closer. This one will move closer to compensate for this one. So whatever charge that results in here is compensated for the other charge, and the same thing for the other 2. So this is nonpolar. Okay, because of the symmetry. Usually this the polarity has to do with the asymmetry. So in this case, there is symmetrical structure, so we don't have a problem with it. Okay, that's exactly what you burn in the burner. Okay, that's methane. So multiple covalent bonds are possible. Let me explain how that works. Okay, oxygen and oxygen, both of them have 1 electron outside that is available. So what they do, they share their electrons in this case. And you will have 2 covalent bonds between the 2 oxygen atoms, and you have oxygen gas, and that's how oxygen gas is formed in here. Same thing in here. Actually, the carbon has 4, but the oxygen can take only 2 at a time. So one oxygen takes 2 and the other oxygen takes 2, and that is what carbon dioxide is. Carbon dioxide also is symmetrical in this case, and it's nonpolar. Okay, nitrogen also is nonpolar because of the symmetry, but it has 3. Each nitrogen has 3. So the 2 nitrogens now, they share their 3 electrons with one another, and now you have the nitrogen gas. So in the covalent bond, this is H2 hydrogen gas. Then this is basically the story I was talking about in terms of how the distribution of the actual electrons is. In a polar molecule, though, there is one that brings them closer to it than the other one, okay? They're unevenly shared. One of them has more affinity. Actually, the dots are closer to the fluorine than the hydrogen in this case. So you're left with a net positive charge in here because you still have the ion that is positive in here, and the ion now is overwhelmed by this negative charges in here. So you have a negative charge in a sense in here. Okay, this is the rule in general, because yeah, you have more protons in here, but the size of the atom, you have a lot of electrons that shield the protons in here and makes the attraction a little less. So the electrons tend to move higher, closer to this side in here, where you have a lot of basically protons still, and they attract that outside electron closer to them. Okay, so that is how the electron affinity is, and that is how the electronegativity is formed, and that is how polarity is explained in here. So sodium and fluorine, it's polar. Actually, it's not polar, it's ionic. It brought it so close that it lost it completely from the sodium, and it's gained come in here in the fluorine. So in this case, this is ionic. Look at the size of the arrow. It's too much, okay? So this is completely basically ionic structure. In the case of when there is a weak, there is still the hydrogen in here is still holding because there is only one proton, yes, but it's so that electron is closer to it, so it's pulling on it. Remember, the electrostatic force is inversely proportional to the distance. Since the distance is less, so it's attracted more, but the fluorine is still overwhelmed. It still have a lot of protons inside, so it's going to bring them closer, but not too close, unlike in this scenario. So in this case, it is polar. There is a net negative charge next to the fluorine and net positive charge near the hydrogen. In this situation, both of them have the same strength. This is completely non-polar. Okay. Here is a question, which is a very, very interesting question if you think about it. It's a very, very important question too. You have carbon dioxide, which is extremely heavy. You have carbon that has 12, its atomic mass is 12. Oxygen, its atomic mass is 16. 16 times 2, that is 32, plus 12, that's 44. So you have 44 atomic masses. If you want to multiply them by 1.6 times 7 to the negative 27, you're going to find it extremely heavy compared to H2O. H2O, the hydrogen is only one atomic mass. You have two of them, so it's 2 plus 16 for the oxygen, that's 18. This is 18, this is 44. This is more than twice heavier than water. Yet at room temperature, carbon dioxide is gas and water is liquid. Although the liquid in this case is a lot lighter than the carbon dioxide. So what's going on in here? Why is this? The heavier can float, becomes a gas. If you take carbon dioxide and put it in water, actually it comes up, okay? But if you do and the water actually sinks. So what's going on? Although this one is extremely heavy, more than twice heavy than water. More weight, more mg on it. So the explanation has to do with the polarity, actually. This is polar, H2O is polar. This one is non-polar. That means the carbon dioxide and carbon dioxide, they don't interact with one another. That's why the two molecules in here, they are free to float wherever they want to. H2O, though, is polar in a sense that one of them is slightly charged and the other one is slightly charged, and they face one another and they hold on to one another. So there is more interaction between the different water molecules than between the carbon dioxide molecules. So in this case, the carbon dioxide molecules are free, and there is no order between them. There is basically, and these ones, they still have some order between them. They interact with one another. That is the explanation for this one. If you just take the masses by themselves, the picture should be reversed. This should be somehow sink, and this should float, but it's the opposite. This is the second item of discussion. Compare carbon dioxide to water in terms of masses, and why carbon dioxide is a gas at room temperature and water is not, is a liquid, okay? Although the picture should be backward. And the answer has to do with the polarity. Water is a polar molecule, meaning that the different molecules interact with one another, whereas in carbon dioxide, it's non-polar. Does this make sense to you guys?
So for the carbon dioxide, on an individual basis, like a one molecule of carbon dioxide, the carbon dioxide is heavier than one molecule of water. However, when they're put in a room together, the water will use its polarity and they'll interact more.
Okay, with one another, whereas the carbon dioxide has non-polar. You put them next to one another and they have no idea that somebody else exists near them.
Yeah.
Makes sense. Yes? Everybody yes? The other guys?
Sorry. Do we have an item of discussion for today?
This is the second item, yes.
Okay.
Okay. Did you remember the first one?
I missed it over. My internet's been really off today. I'm sorry.
The first one has to do with basically classifying the different kinds of chemical bonds. Okay, remember I said ionic and covalent bonds, they have a similar strength. And then metallic bond is actually weaker than those. It's a lot weaker. And then we talked about polarity. Polarity in here, you have the case, like this case, for the case of water, you have a dipole and a dipole interacting with one another. You have a dipole inducing a dipole in another one. So otherwise, the other molecule is non-polar, and this one is polar. So it's going to induce one in the second one. Now you have a weaker interaction than a dipole-dipole. And the third one, you have two heavy molecules that are otherwise non-polar, but somehow they induce polarity in one another, and they become induced polarity interaction. So those are the item number one. I know it's probably a mouthful, and you might have to come in here and write it down to be able to account for it. And the second question was related to carbon dioxide versus water, and carbon dioxide versus water is carbon dioxide is a lot more massive than water, yet in room temperature, carbon dioxide is gas and water is liquid. And the reason is, the carbon dioxide is non-polar. You put them next to one another and they don't interact. Water molecules are polar, so you put them next to one another and they start to basically stick to one another because of their polarity. So that's basically how you explain this. So those are the two items. Okay, very good. Okay, so let's continue. Still have quite a few things to do, and I know the time is running out. So this is basically what I was talking about, the polarity. In the case of carbon dioxide, you have, even if one of them has more affinity toward the other one, it's still, this oxygen pulls on the same strengths as the other one, and now you have them canceling one another. So that's why it's non-polar, okay? Whereas in the case of water molecule, in this case, you have a net positive charge. Actually, it's not symmetrical as the other one, at least in this direction. So there is a net charge in here, net motion of the electron closer to it. So it has to do with the configuration, actually, of the molecules, okay? So this is not symmetrical 100%, whereas there is a positive charge in here. So if I bring another water molecule in here, remember, I have a net positive charge near the hydrogen, and I have a net negative charge near the oxygen. So this molecule will turn itself so that to bring one of its hydrogens closer to the oxygen in here and have this weak interaction. Dipole-dipole interaction. And this is a dipole-dipole interaction, and this is how the liquid water forms, basically. And actually, solid water will form actually in far more organized fashion using the same forces.
Isn't that a hydrogen bond, like the temporary one?
No, this is not a hydrogen bond. Hydrogen bond, actually, you share the hydrogen between the different molecules. This is a dipolar interactions.
Okay.
Okay. Hydrogen bond, actually, you share the hydrogen. Like, for example, the long chains in organic chemistry, that's where you see the hydrogen bond. And we're going to come into it later on, okay, especially when we do organic chemistry. But at this point, this is actually dipole-dipole. So the two atoms, they rearrange themselves. This guy's in here, they do whatever they want to do whatever dance you like to do it. They will never, carbon dioxide will not influence another carbon dioxide because they don't have the means to. They don't have any kind of charges in it. This ones do. Okay. Water has such a relatively high boiling point because it is heavy, no, it's transparent, no, because molecules are so sticky. You really have to break these bonds in order to get into a gas form. You guys understand? Because of there is this stickiness, they stick to one another. They are actually they are glued to one another via these interactions, dipole-dipole interactions. Then once you raise their temperature enough, then they lose that. They become so agitated. They become so, because of the high temperatures, then that bond breaks. Okay. And the more heat you add after that point, after 100 points, is just to break more and more bonds. That's why the latent heat of boiling point in this case has to do with that heat breaking all of the different bonding. Once it's broken, then the temperature starts to rise again. So that is how the phase transformation happens. So the phase transformation, you have this bond as the temperature is rising. For example, it's 95, you put it at 96, so they become agitated more and more, but as they're still connected, still water. 99, it's still water, but they're extremely violently agitated. At 100 exactly, this starts to break. So some of that energy breaks this one, another energy breaks this one, another amount of energy, and you don't increase in temperature anymore until you break the last bond in it, in the water, and all of it is evaporated. At that point, the temperature now, if you keep on boiling that gas, that vapor, is going to start to move faster and faster, just like carbon dioxide then. Okay. Ion dipole interaction is kind of a strong interaction, and that is because of the fact that you have ions in here that have very, very strong charges in them. So for example, sodium, which is ionized, will interact with the dipolar water in this case, and will stick to it. And that's how the solution of NaCl is formed. That's how you take salt and you mix it with water, and that is how you have this solution in here. Now, chlorine, on the other hand, will attract the positive side of the same water molecules. So NaCl is still salt. So when you dissolve it into water, this is what's going to happen to it. So there is an ion dipole interaction, which is actually stronger than the rest of the other dipole interactions. Okay? So that is one way of doing it. The other one is a dipole-dipole interaction. This is similar to what we were talking about in the case of water. So this is the dipole-dipole interaction between the two. So the positive side of this water molecule, positive delta in here, will be attracted to one side of the negative delta on the other side from the water, and so on and so forth. And the molecules start to rearrange itself. The molecules start to rearrange themselves to become closer and closer from one another. So since this is weaker than the other one. And then you have the dipole-induced dipole. So one of them is otherwise neutral, does not have anything. Like, for example, the oxygen in here, oxygen molecule in this case has no polarity whatsoever, because both of them have the same strength. But if you bring it closer to water, water on this side induces a positive charge on this side. So brings the charges closer to it, if you wish. Oops. And then the oxygen molecule now rearranges itself so that, yes, one positive moves in here closer to compensate for that, but then the negative will move to the opposite side to retain the zero charge in here. So now water has attracted in actuality and glue itself to the oxygen molecule that does not have any polarity. And this is an essential operation for life underwater, because fish relies on this interaction to extract actually the oxygen molecule from this mixture and get rid of the water. So if you have fish under the water in the ocean, what they do, they breathe in the water and then get rid of the excess of the water on their skin or gills or whatever that process is, and retain the oxygen. So in an oxygen poor water environment, you should not see life. You should not see life that depends on the water, that depends on oxygen. Like, for example, living organisms like animals that breathe oxygen, part of their biology. So fish relies on that water. Yes, could fish drown under water? Absolutely, if that water is not rich enough in oxygen. This interaction is super weak though, but it's just enough to sustain a lot of life under the oceans. So this is a dipole-induced dipole. So this has no dipolar structure. This is not a polar molecule whatsoever. But near water, it becomes that way. It's induced. It's not real. It's induced. Now, this molecule is glued to the water, floats inside. Fish take that mixture, get rid of the water because it's not going to breathe it. It cannot use it in its lungs. It uses the oxygen that is extracted from there. Okay. So is it possible for fish to drown? Absolutely. Well, yes, when the water contains very little oxygen, okay? Not this oxygen, do not confuse the two. You need a chemical process to remove this oxygen. It's not possible, okay? Not because water has oxygen in it, not because of H2O. That is not the case. It's because of the oxygen that gets stuck through this dipole-induced, dipole-induced dipole interaction that is being used. It uses O2, so it's not really going to use the other one, okay? So this is not true. So C is not correct, okay? So this oxygen is soluble basically into water because of the induced dipole interactions, and the correct answer is C. Here is another one, the last one of these processes, which is really the dipole-induced dipole. So both of them are induced dipole, induced dipole, induced dipole. For both of them, like the argon in this case, becomes like O2 in this case, is because of the fact that you have them super big. And it's like, for example, the typical example in here, when you have a big boat, a cruise line, for example, one of those things that they use them, you can still afford to have a bunch of people gathered together in one area of the boat. The boat will not flip. The boat will not shake. The boat will not will be safe. So in this case, you have a lot of charges go on one side, and the entire thing stays retains its energy with no problem whatsoever. Now, if you take the same group of people and put them on a small, for example, boat that barely can contain them, you cannot afford everybody to go on one side of that thing. If they do, then the whole thing will flip and it's not going to be correct. So this is the similarity in this case. Usually it happens for large atoms like this one, and they have induced basically interactions with one another. Both of them are induced though. So this is the weakest of all of the interactions in here, okay? Because it can be easily broken. Yet it plays a major role, for example, in the case of the iodine in here becoming solid in room temperature, okay? And fluorine molecules in this case. And Teflon basically have this long chain of organic matter. Instead of hydrogen in here, you have carbon. I mean, instead of hydrogen, you have fluorine. And because of this dipole interactions in here, or the lack thereof between the fluorine atoms, you can still have this non-sticky material that you can use. This is Teflon actually for cooking materials that you can cook your eggs, for example, without being stuck to the surface of the pan. Okay, this is actually used also by the gecko, for example, which is this induced dipole interaction with the skin, which is made up of very, very tiny hair with the surface, for example, of glass, and it can support itself, which is kind of basically a big technological advantage if you can make one of those, okay, with only one finger, with only one toe, okay, it can stick itself to, and its entire mass, its entire weight can be supported that way. This is fascinating. Actually, there is interest in this technology. If you can ever develop it, imagine the what you can do with it. You can climb basically a building straight up with it, okay, if you can somehow do it. And buildings are not as slippery as glass, so, okay. Which of these molecular attractions takes the least amount of energy to break? Obviously, the correct answer is the induced dipole attractions, okay? Okay, I know this is the entire chapter. Please watch for communications. I'm working on them. I know some of you have some stuff that's related to the exam and things like that. That is not official yet, so you will have your exam immediately after spring break. There will be the exam review also. So I'm hoping to finish that hopefully no later than tomorrow afternoon. Worst case scenario, by Saturday, you should have details into what you need to prepare for. The review is not going to be due in the spring break, so you'll have time to finish it, to enjoy your spring break, but also try to go through it at least once. Hopefully during spring break. If not, immediately after spring break. Tuesday after spring break, there is no class, and that is dedicated to this review. And then the review is actually going to be due on Wednesday. Do not finish it by Wednesday, though. You're supposed to finish it before that, because just in case if there is a problem or an issue, you can tackle it, because I'm not going to extend the review whatsoever, because the exam is going to be due on Thursday after, which is the 22nd of April. Okay. I'm going to stop the recording, and I'm going to see you guys after the spring break. So enjoy your spring break. Have a safe, which is very important nowadays, and happy spring break. Okay.